Hey everyone, welcome to Professor 3 Mac. Today I'm going to show you how to perform lightning strike simulation on a wind turbine composite blade using ABAQUS CAE. The problem is shown on the screen, so I will quickly go through it so that you decide if you want to continue or you want to leave this video for now. So we will use a simple composite laminate, which is shown here. In this case, I'm going to use 4 plies, which will be oriented at 45 degrees, 0 degrees, minus 45 degrees, and 90 degrees. And lightning will strike somewhere in the middle of this laminate. And we will see how the composite really responds to this lightning strike. Please note that I have made this simulation at a very high TRL level, which is like technology readiness level. So you can use this in the industry where you use FEA to simulate this kind of response. And you try to see based on isotherms or temperature profiles that, okay, what could happen to your structure based on the temperature predictions caused by the lightning strike. It's an active area of research, as I said before. So people are still working on how your composite really responds to the lightning strike at high temperatures. For example, delamination is a big problem at that temperatures, and electric currents, pyrolysis, ablation is another issue. Fiber breakage and sublimation at high temperatures is also under a lot of investigation. And there are some other aspects as well. So there's a long list to that. So you can see it's a highly active area of research, and one can go in any direction if they are interested in. So what we're going to do, we're going to try to simulate that plate, which I just showed you before. And there will be lightning strike in the middle of the plate. I will use this well-known relationship to define the lightning strike curve, which is electric current as a function of total time of a strike, which is shown here on the slide, and it will look something like this. And I will apply a total current of around 20 kilo amperes, again taken from literature. If you're interested in which literature I have used for this curve or other material properties which are shown on the right hand side, then please comment below and I will share the link with you guys. So temperature wise, analysis wise, we will be doing a couple thermoelectrical analysis, and we will have to define temperature dependent properties in this case because it's a high temperature process. And we will be defining electrical conductivity, specific heat, thermal conductivity, density, and thermal radiation, which will all be varying as a function of temperature. Again, why we need these quantities? You might have to go and look at the documentation for solving the coupled analysis for thermoelectric cases, and that will give you an idea, okay, why do we need these properties when you look at the fundamental equation. So this is pretty much it from finite element side. We will have a composite plate with 4 ply, as I told before. Lightning will strike onto it in the middle. I will define the lightning strike as a current, electric current as a function of time, and we will define the material properties. While based on the experimental results and data from literature, we're going to use these boundary conditions. It's a very high speed process, around 60 microseconds. So we are assuming everything to be adiabatic in this case, while the top and the side surfaces can have thermal radiations or heat transfer due to radiation, while the sides and the bottom surface will have a potential of 0 volts because we have electric current, so we need to define the voltages as well. Also, the electric current, which is due to the lightning strike, will be acting at somewhere here at this point, and I have already shown you the curve for that. So let's move into ABAQUS and see how we can do this. See you on the other side. Okay, let's get started. We will first start with creating a 3D laminate plate. So I will create a 3D deformable solid object. Let's call it laminate. For example, in this case, this will be a 3D select deformable solid in extrusion. I'm going to create a plate using the rectangle sketch, and the sketch will be 150 millimeters by 100 millimeters, and I will give a thickness of around 5 millimeters. I'm going to make everything in meters, and so that all the other units will be consistent with that. So start with 0, 0, and then I will give a coordinate of 0.15, 0.1, and that will give me that rectangle, which is 150 millimeters by 100 millimeters, as you see here now. Now I'm going to give an extrusion depth of around 5 millimeters. So let's give this value of 5 here. Press OK. Oops, I think as I made everything in meters, so I need to convert this 5 millimeters to meters as well. That's why you see this strange sort of bar. So let me go back to the extrusion. As you see on the model tree, you can go to the features and then double click on solid extrude. It will bring back the depth thing, and now I'm going to convert this 5 to 0.005 meters because everything is in meters. I just forgot to convert that. And once I press OK, everything goes back to normal. Abracadabra. So now everything is done. What I have to do now, I have to create 4 plies. As I told you, 45 degrees, 0 degrees, minus 45 degrees, and 90 degrees. So I'm going to use this partition cell option, defining the cutting plane. And in this case, I'm going to use 3 points. So I have to define 3 points on a plane that will then be used to cut the sample. So in this case, I'm going to first start with the midpoints of the cross section. In this case, I'm defining these 3 points. And so here you see, now the create partition button is pressed and you see the partition is being created. So now we have 2 plies. I need to create 2 more partitions so that I can have 2 more plies. So let me again select the section. 3 points I will again select. And now I will start to select the points. So let's first do this side of the ply, and I will create a partition in this part. Select the second point here. Now let me try, it's giving me a hard time. Okay, done. So now I'll go to the next one, and this will be the 3rd point as you see on the screen. So it's the 3rd point. So once I have done this and I press create partition, and I have another partition. So now I will do the same to the back ply, and I will divide it into 2 more plies. 3 points again. I will select the midpoints again along a plane. And that's what I have done here. So first point, second point, and the 3rd point. So this will give you an advantage that you don't need to really bond each of the plies. If you make each ply separately, you can still assemble them in the assembly module, but then you have to tie them together. Again, there is a video on our channel on how to bond different components, so you can still use that, but then it may increase your computational time. So now I have 4 plies, as you see, very nicely divided into 4. Again, these are just arbitrary. I just selected those. You could have 8, 10, 12, depending on your experimental setup. Now let's go to the property module and define the material properties. So I will create the material properties. We call it material 1. And we will first start with, let's say, density. Maybe we'll start with density. And we will define a temperature dependent density. So we have to click on this. Now we have the table. I will just copy paste the data as I mentioned before from the literature, but if you need more information where I got these properties, then please comment below and I will share the link to the paper. So here is the density as a function of temperatures. Then I will let's define the next thing, which is conductivity, thermal conductivity in this case. So let's see how we can do that. So select the conductivity, again select the temperature dependent data, and also composites are orthotropic in nature, so we will define conductivity as orthotropic material. So we need to define 3 coefficients in 3 directions. And anisotropy will require 6, while orthotropic will require 3. So in this case, orthotropic is okay for the composites. In this case, CFRP composites. So again, I'm copy pasting as the temperature dependent properties from the literature. So these are the properties I have used. So which will be directionally dependent. So we need to apply orientation later on. Now we define the electrical conductivity, same temperature dependent data, and also orthotropic. And again, we will define these properties which are dependent on the orientation as well as the temperatures. And here are the values. Everything is in consistent units, which means we are working with SI meter units. The last thing which is left now is specific heat. So again, I will define a temperature dependent specific heat. And it doesn't involve any anisotropy, so we're just gonna give the same value in all directions. So I think that's pretty much it for the material properties. So now we're gonna press OK. Yep. Close this, and we're gonna create solid sections so that we associate these material properties with this composite laminate. So yeah, so we'll select the assign section, assign the section, and then select the specific section with material one properties. The color is changed, so everything is assigned correctly. Now we have to define the orientation. Since we have defined the orientation dependent property, so we need to define the orientation of each ply. In this case, we select the first ply, use the default orientation, which is the global XYZ, and I'm going to select from global to coordinate system. And then maybe we give an orientation of first one as 45 degrees. There you go. And I think we need to do it for our about axis 3, which is a z-axis. So let me first check where is the z-axis. So z-axis is orthogonal to the plane. So let's select z, and now you can see it's correctly oriented. Okay, now let's define for the second layer. We will select the second layer now, and we will do the same exercise what we did for the first layer. Select the coordinate system, then select axis 3, and in this case the orientation should be 0 degrees, so I will give a value of 0. And that's pretty much it. In this case, because nothing happens, then I will select the third one. So let me select the third ply, and here you see again the same story. In this case, I will give a orientation of minus 45 degrees. So our third ply is also defined with an orientation of minus 45. As you can also see in the screen, how our coordinate system is rotating. And now the last one, which is 90 degrees. So depending on the orientation, you will see later on how the temperature distribution also changes, which is also dependent on the orientation. So again, in this case, we will give, let's say, 90 degrees. Again, these are arbitrary. You can select whatever you want based on your own data. So I think properties are now correctly defined with orientations and also orthotropic with directional dependence as well. So here you can double check if your orientations are defined correctly for each layer, and you can see how the orientations look like. You have to go to query and then select material orientation and select each ply, and each ply will tell you how the orientation looks for individual plies. In this case, we are modeling everything as solid. So this is for the other ply, and you see it's not oriented because it was 0 degrees, and you can keep checking all of them if everything is defined correctly or not. So once you are all sure that everything is fine, then you can go to the assembly and we can bring everything here. In this case, we call the whole thing as one part, so we just have to import instance the whole part here. As one thing I forgot to mention, because later on we will have to define the current in the middle of the part, so it might be useful that we should partition this along this plus sign here, so that we can define the properties in the middle correctly. So we can do it. It's better, I think, to do it in the part module. So let's go to the part module now. So let's select the partition option, and I will select the face which I need to partition, and I will again select 3 points, and in this case I will select the 3 points on this plane. So 3 points now, so I will select 3 points on this plane. I need to cut. So first is this one, and the last one we can select on the other side maybe, so it will give a kind of a plane in the middle. Here you go, and then create partition, and abracadabra. Here you go. And I will do the same in the vertical direction as well now. So you see, it's only dividing it into top. You will realize this later on, that we need a central point in the middle of this sheet to define the boundary conditions, which are loading, which is basically the lightning current. And it will help us if we have a division there and we have a point there. So now I will do the same for in the normal to the previous cutting direction, and in this case I will select this point, second point here. And if I can zoom out, I can select anything related to that. Yeah, this should be fine as well, maybe. And that's pretty much it. So now we have the plane and we have a point there where we can apply any loading if it's a point load, which is the case in our present scenario. So now we go to assembly, we have the part. Now we go to the step, and in this case we press create step button, and we will select, I think we need to find the coupled thermal electric analysis. So let's scroll up and see where it is, and you can see it's there. We are doing coupled thermal electric analysis. The total time, as you remember, is 60 microseconds. So it will be 6 exponent minus 5 seconds in reality. And I'm going to give a very large number of time increments here, so that it doesn't stop after a certain number of increments. And the initial time increment, again, your choice, but I will go with something smaller than 6 exponent minus 5, which is the total time. And also this minimum time increment I'm specifying as minus, let's call it 6 exponent minus 15 or something, so that if it struggles, it will reduce the time increment and it's small enough so that it doesn't stop. And here I'm just selecting minus 7. Again, this is just trial values. You can use your own as well, wherever you think this convergence will occur. I'm also allowing the maximum temperature to be 10 degrees. You can also select 1 degree. It might slow down your simulation. And I'm not really going for accuracy right now. I'm just going to show you the whole process of doing the simulation. Here is the output. You can ask for other outputs as well, but I'm going to go with the default because we already have potentials, heat fluxes, and nodal temperatures. Maybe we can select temperatures at integration points as well, so if you want. But yeah, so you can read all these description of the output variables as well. Nodal temperature, maybe select temperature for elemental temperature if you need it later on. That's pretty much it. And you can also control the output. If there are too many number of increments, your file size can be big. So I'm just selecting after X input, and I say, okay, after every 1 exponent minus 7 seconds, write an output, rather than writing at every increment, which was the case as a default. I will do the same for the history output, and in this case I have already done that. Sorry, this is the field output I have selected. Now I will go to the history output, and I will do the same here. So rather than writing after every increment and making the output file size really big and maybe slow down the simulation as well, I will just ask it to write after every 1 exponent minus 7 seconds. Okay, now we go to the interaction, and in this case we have to define the interaction properties. So in our case, the interaction properties will be based on the fact that we need to define radiations. So we need to select, in this case we have defined the surface condition, the surface radiation. We have to select step 1 as you see here, and then we will select surface radiation. Press continue. Select the surfaces, as I told you, top surface and the side surfaces will have thermal radiation or heat transfer due to radiation. So once you select that, you need to specify the emissivity, which I am selecting to be 0.9, again from a literature. And ambient temperature, and I am selecting it to be 298 Kelvin. So again, remember, I define everything in Kelvin, so I'm keeping everything here as Kelvin as well. Press OK. And that's it. And now I have to do the same for the side surfaces. So I will go back again, surface radiation. I will select the surfaces individually. Again, you can find a shorter way quicker way to select these surfaces, but I have selected by angle, and this way I can select the surfaces quicker. Otherwise I have 4 surfaces on every side because of the ply division partitions we have created. So I'm going to do the same on this surface and this surface. So now I have all the 4 surfaces collected. So now I'm gonna give an emissivity value of 0.9 again, and the absolute temperature to be 298, which is around 25 degrees Celsius, and press OK. And now we have defined our interactions, which are the radiation, thermal radiation. Now we go to the loading and boundary conditions, and we will start defining our loadings and boundary conditions. So our load will be at the center, where we will define the lightning current. So let's go to the load module, create load, and in this case we have to define concentrated current, which is a lightning strike, and we will select this middle point. If we had not created these partitions, then we might be struggling to have this point there. So you see, that's why I created the partition like that. Now I'm going to give a value of 20,000, but this 20,000 will be following that curve for 60 microseconds. So I have to define that amplitude function as well. So that's what I'm going to do now. Use the data again, which is here, as I showed you before. So this is the curve, and I have created an Excel file for that. So I'm gonna use that data to define those properties. Do that now, tabular, continue, and I will select the amplitude function from there. Here you go. So my amplitude function is now there for 60 microseconds. And now we press OK. And now we have to select the amplitude here as well. So after doing that, so we have this lightning strike in terms of current is given there as a function of time. Another thing is basically to define the voltages, as I told you, on the top and on the side surfaces and the bottom surfaces. So we select the electrical and magnetic, and I select electric potential, and then we will select the individual surfaces and apply the electric potential to be 0. So let's do it. It will be tedious because I have to select each individual surface here for each ply. I think zooming might help you. So you see now I can clearly see what I'm selecting here. So I've selected the 4 surfaces. I will do the same on the other corner as well. Zoom in and do the same thing on this side as well. There you go. So hopefully these external surfaces, which are the side surfaces, are selected, and we have defined a potential there. If you select internal surfaces, that may cause some errors, and within the numerical values you get for temperatures, etc. So make sure that you select that. Now I'm giving the value of 0. So now everything is correctly defined, I think. Only thing is the back surface, we also have to give a potential of 0 volts to on that surface as well. This should be easy because it's only one surface. We just click on it, press done, give a value of 0, and that's pretty much it. So now we have the potential defined there as well. So I think all the loading and boundary conditions which I mentioned at the start are now defined, and now we have to also assign the initial temperature because we are at the room temperature. So I'm going to select temperature for initial tab, and we will select now the whole laminate plate, and I will specify a value of 298 kelvins. So again, I'm working with kelvins everywhere. So my absolute 0 will be 0 kelvins, remember that, and not minus 273 degrees Celsius. Now I'm going to mesh everything. Need to select the part first and then define a global seed. Again, I'm not optimizing the mesh here. I leave it for you guys to play with the mesh and find which mesh gives you the best results. I'm just selecting 0.025, and now I'm gonna mesh it. So this gives me a total number of elements of 9,600 elements. I need to select the respective elements as well, which I need. So I will select the element type, standard linear, and then I have to select thermal electric option here in the family, and it will automatically give me the default elements, which is okay for the time being, which are brick elements, since I'm modeling everything in solid. Okay, now we go to the job. We'll create a new job and we call it, let's say, you have to select the respective model, and now we call this model as should we call it, maybe call it 4-layer laminate. So we remember that we did 4. Also precision should be full because we are dealing with very small and very large numbers as well, so it's better to do that. So now we submit the job and start monitoring, and I will get back once the simulation is finished. You see the simulation is finished without any problems. So now let's go to the visualization module and see how we can look at the results. Okay, let's look at the temperatures. You can play a video or animation and see how the temperature evolves. I will also show you how you can see temperatures in different layers. So we have 4 plies, and I will show you how you can see the variation in temperature in different plies as well. Look at different plies. So let's first remove the top ply. I will select create group, select this ply at an angle. So yeah, let me select this ply, press done, and then press remove button here. If I can move it up slightly, yeah, so you see it's a remove button. I will press this and the ply is gone, and now you can see the temperature has reduced to 935 kelvins, and distribution is changed as well because you remember the second ply had an orientation of 0 degrees. Now I will remove this ply and see what has happened in the third ply. I will remove the second ply, and you see minus 45 degree has a much lower temperature, around 306.5 Kelvin, and also distribution is different. Now let's look at the last ply quickly, and you can see if I remove that, then it was 90 degree ply, and you see how the distribution look like, and it's almost the room temperature. So you can see that this 4 plies are more than enough in this case, because after 4 ply you will have room temperature. But again, we haven't accounted for any sublimation, melting. Sometimes people have reported that epoxy can disintegrate or decompose after 260 to 300 degrees Celsius. So again, you have to look at those as well, that what sort of properties you have used. But in this case, I hope you have learned that how you can really assess the damage due to the lightning based on the temperature profiles happening in different plies. So I'll see you next time in another video, and hopefully if you comment below if you need anything more on this video, because I just made it in a quick time. And as I said, it's a big area, so if you need any help, then let me know. Bye for now.